So also note that I've cheated and I've already written something on the board while you were coming into the room, but that's a reminder of Sylvie's talk. I mean, a reminder of things from Sylvie's talk which I want to use in my talk, and so you can stare at them again when I get to it. Okay, so for a language L, we've defined the notion of an L theory T. So an L theory was just a collection of sentences from L, so a collection of formulae without free variables. And we defined what it means for a theory to be consistent. This meant it had a model. And we defined the notion of completeness. This meant there was a consistent theory which proved, which which entailed every sentence or its negation. So, or in other words, such that all of its models are elementarily equivalent to another. And as an example, we have the L-ring theory ACF0 or ACFP, which both also occurred in Sylvie's talk, right? This means every polynomial of every non-constant polynomial, I'm a field, every non-constant polynomial has a zero, and I have characteristic 0, which is axiomatizable only by infinitely many sentences, as I think Sylvie argued, or may well have argued in her talk. And this says I'm an algebraically closed field, and my characteristic is a given prime P. Okay, so now Sylvie also mentioned in her talk the compactness theorem. Maybe I want to say these, as Sylvie said, they're both complete. That's called Tarski's theorem. And I prove this in two ways in this lecture and the next lecture. So maybe both in this lecture if I'm really fast. Let's see. But for the moment, take it as a spoiler that there. I'll use it in a moment, but I'll prove it as well sooner or later. Okay, so the compactness theorem states, Sylvie already stated it as well, an L theory T is consistent if and only if every finite subset is consistent. Okay, let's start by giving corollaries before I prove it. Maybe I call this theorem in parentheses compactness. So I'll aim to at least give you an idea of the proof. I don't want to say I'll prove it in every detail, but okay. So what can I do with this? So this morning, when we defined the p-adic integers and the p-adic numbers, I said, well, currently I only have constructive methods of showing something is first order. I can't show anything yet which isn't a first order property. So I now show Archimedeanity is not a first order property. So there are non-Archimedean models of the theory of real closed fields, which I wrote on the board this morning. So what does Archimedeanity mean, right? In the reals, for every positive real number, there's a natural number which is larger than my positive real number. I guess this is also true for every negative real number, if you like. So the natural numbers are cofinal in the reals. And but this is not a first order property, as we show now. So what do I do in order to look at this? I'll introduce a new constant symbol. So consider this is like a standard trick, which will haunt us in further lectures. So consider the language of ordered rings together with the new symbol C, where C is a new constant symbol. So in the language of ordered rings, there were two constant symbols, namely 0 and 1, and I just want to use a different symbol to 0 and 1. Right, this is not a... And now I look at the theory T, which says that is a theory of real closed fields, together with the statement that C, for every n I look at the statement saying that C is greater or equal to 1 plus 1 n many times for every natural number n. Okay? And now every finite subset of this obviously has a model, because I can just take the reals as a model and assign C to be larger as whatever the biggest number of n's occurs here in my finite subset. So then T is finitely satisfiable. That's another way of saying every finite subset of T is satisfiable.
Could you raise the bar?
Yes, I think I can. So the compactness theorem tells me that T has a model. So there is a real closed field which is non-Archimedean. Okay, similarly, Archimedeanity is also not axiomatizable in the language of ordered abelian groups, right? I mean, when you have an ordered abelian group, Archimedeanity would be the property for every epsilon and delta, say both positive, there's an n such that n times epsilon is bigger than delta. And again, you can do a similar argument. Another corollary, which Sylvie also alluded to, but which I want to make a bit more precise, is a Lefschetz principle, namely the statement is in a ring sentence holds in almost all FP out. If and only if it holds in C. So it holds in almost all, just for the moment means all but finitely many, and so it holds in algebraic closures of sufficiently large finite fields if and only if it holds in the complex numbers. So let's assume a sentence phi holds in C, right? You really remember this was my notation for this, or this is the standard notation for this. And now, by the completeness of ACF0, which I vow to prove later, this means that it must hold in every model of ACF0. And this means ACF0 together with not phi is not consistent, because every model of ACF0 knows that phi must hold. So this cannot have a model. So the compactness theorem tells me if it's not consistent, already some finite subset of it must be non-consistent. So there's this a sigma subset of ACF together with not phi, and now I've not written the zero, but I'll now write I'll write the characteristic zero part separately, just so we can read it better. Not, this is whatever, p times for every p prime, or n times for every n natural number, I don't care. So finite, which is not consistent, but I mean, obviously, only finitely many of these conditions can occur in my finite subset, right? So only finitely many characteristics are excluded here. So this means for almost all p, apart from the finitely many which I excluded, ACF p together with not phi is not consistent. And so now completeness of ACFP, well, maybe I don't actually need completeness of ACFP again, but certainly it doesn't hold, it doesn't hurt. The algebraic closure of FP knows that phi holds for all but these finitely many primes which were excluded. So for almost all P. Okay, now again you can use not phi to go the other way. So now you need to go one way. So this Lefschetz principle in particular implies X's theorem, which aka X-Grothendieck, so Sylvie told you to Google it, so I'll give you a bit more information than that. I mean, okay, Sylvie told you to look it up. Namely, every so the statement is every injective polynomial map. So a polynomial map is given by something like a multivariable polynomial. F from C to the N to C to the N is surjective. And you do this by proving it, right? I mean, you prove X's theorem, and so the proof, I ultimately the proof as an exercise, but the real thing is that you need to translate this into a first order statement, and that's not a single first order statement, but it's countably many. So for a polynomial map, you need to fix here the n, the arity, and you need to fix the total degree, say m. And then you can say for every polynomial map of degree n and, of total degree m and arity n, this is now, you can translate this now into a sentence in the language of rings, and then you check it holds this is a statement which holds into every algebraic closure of a finite field, and the reason why it does is that that it holds in every finite field. Right? Every injective map from the power of a finite field to itself must be surjective because the field is finite. But then an algebraic closure of a finite field is just a union of finite fields, and an injective polynomial map restricted to one of these finite fields must again map into that finite field because of, well, whatever, finite fields are closed under multiplication and addition. Okay, so now I want to prove the compactness theorem, or at least tell you how it's proven. And very kindly, Sylvia has already done some work for me. So recall from Sylvie's talk that when X is an infinite set, I can look at ultra filters on X. I guess I can also do this for finite sets, but then it's less interesting. I'll tell you why it's less interesting in a moment. So an ultra filter is a collection of subsets of X, which you should think of as large sets. Namely, the empty set is not large. If A is large and and A is contained in B, then B is in particular large. And if you have two large sets, then the intersection is large. So far, I'll use this in a moment. Let me at least keep this in name. This is a notion of a filter, and then an ultra filter is somehow a maximal filter. Namely, it's an ultra filter must contain every set or its complement, every subset of X or its complement. That's an ultra filter. In principle, this also occurred in Sylvie's talk, is an ultra filter which is defined by membership of a singleton. So all subsets of X which contain a given singleton little x. And as soon as your ultra filter contains a finite set, it's easy to show that it's then in fact a principal ultra filter. So this is why on a finite set somehow only principal, aka boring ultra filters exist. But on any infinite set, Non-principal ultrafilters exist by Zorn's lemma because you just start with the filter of cofinite sets and then extend this using Zorn's lemma into an ultrafilter. Cofinite means finite complement. And then Sylvie also defined the notion of ultraproduct, namely if you have a collection of, for every I in X, you have a family of L structures, say AI, it's an L structure for every I in X, then you can look at the corresponding product, namely so this is all sequences from AI modulo an equivalence relation, where the equivalence relation says two sequences are considered to be the same if and only if they coincide on a large set. And the Wash's theorem says that a statement phi holds in first you can turn it into a well-defined L structure, right? You need to work out that the function symbols and the relation symbols, etc., are well-defined, but that's straightforward to set. Check. And Wash's theorem tells you that the statement phi in the language of, or a sentence phi in the language L holds in almost all AI. And now here I mean by almost all, so the complement of those where it doesn't hold, the set where it holds is in the ultrafilter, I should say it positively. And it holds on a large set of I. So it holds almost everywhere if and only if it holds in the ultraproduct. In particular, if all my structures AI are models of a certain theory, then so will be the ultraproduct. Because then the sentences from this theory will hold in every single one, in particular in almost all, to whatever your notion of almost all is. And so Sylvie was taking ultraproducts of finite fields, so I guess it's already, right, one instance of Wash's theorem is in particular that when you take a product of fields here, an ultraproduct of fields, right, whereas a priori it's only clear that the corresponding thing you get is a ring, Wash's theorem tells you, no, it's indeed a field. So what will happen here, when you divide out by this equivalence relation, this means you take the product of rings and you divide out by a non-principal maximal ideal. In this, when you have a product of rings, and in order to turn it into a field, what will happen is you divide out a non-principal maximal ideal. So that's what happens algebraically in ultraproducts, or an ultraproduct of fields, but even more so. Okay, so using ultraproducts, we can now do a short excursion and show completeness of ACF 0 respectively ACFP. Okay, I will so as I give another proof either later today or tomorrow, I'll only do this very briefly, but so what's the idea? Fix a potential characteristic, and now I'm doing P and 0 simultaneously. Let K1 and K2 be models of ACFP, right? And I need to show K1 is elementarily equivalent to K2. What do? I take, by choosing, so I want to say, I can choose an ultrafilter on an appropriate set X wisely, such that the corresponding ultraproducts of K1 and K2 have the same cardinality. It's essentially just choosing a good enough ultrafilter on a large enough set. That's what happens. So by choosing appropriate ultrafilter U on some set X, so on some sufficiently large cardinal, and you can think about how to do this if you like, lambda, we get the corresponding ultra product over K1 right? Where I just take, in this definition, I just take each of the AIs to be exactly, always the same, namely this one field K1. So such that the cardinality of these two others is the same.
You don't like large cardinals, you could also take countable elementary substructures.
Yes, but Sylvie, I haven't proven. So for me, in order to do this honestly, I would have to do the compactness proof via the Hahnke construction. And because I want to prove the compactness proof via the ultrafilter construction, actually I don't get Löwenheim-Skolem as a. I don't get it as a corollary. I know it's whole.
You wanted to quote Sylvie.
Yes, okay. Quoting Sylvie, right? You can do this quicker by applying Löwenheim-Skolem. But I consider this for my course cheating because because I will not prove Löwenheim-Skolem. So, but you're right. I could be quicker.
This cardinal doesn't have to be that large. It's just.
I guess it has to be larger than both of these, and maybe it should be regular.
So you don't need any extra access.
Yeah, you can do this in ZFC.
Yeah, that's what I mean. Yeah.
Okay. So, but then note that as all algebraically closed fields of cardinality greater or equal to Aleph of the same cardinality, as long as it's greater or equal to Aleph 1, are isomorphic, we get K1, this algebra product over K1 is isomorphic to the algebra product over K2. I don't know, I'm sure you know this in your heart, but let's just quickly run through it. So what happens here, if I want to set, so I can look at an algebraically closed field, I can consider a transcendence basis over the prime field, whether it's Q or the algebraic closure of Fp, and two algebraically closed fields are isomorphic exactly if they have the same size of transcendence space. Any isomorphism between transcendence spaces will rise to an isomorphism of the corresponding algebraically closed fields. And so as long as they have the same cardinality, which is greater or equal to Aleph 1, the transcendent space must be the same cardinality as the field, because it's a transcendent space over something countable. So then you have the same cardinality of transcendent spaces, and then you can just find an isomorphism between the fields. You can find many isomorphisms between the fields. And so
transcendent space.
Transcendent space?
Yes.
It's the essentially it's a question of, you could see it as the in this case, I guess it coincides with the vector space dimension over Q. No, it doesn't. Okay, it's the question how many indeterminants you need to. So you start with Q.
Maybe you add something.
This is transcendent space 1. I don't know. This is an algebraically closed field of transcendent space 1. The question is how many algebraically independent elements you find over your base field Q or or Q alge or FP alge. Okay.
It's a maximal algebraically independent subset. It's where there are no polynomial relations between the elements.
Yes. Wait. So now by Watch's theorem, I get K is elementarily equivalent to its own ultra product, which actually is called an ultra power, because this is isomorphic to the corresponding ultra power over K2, which is elementary equivalent to K2.
In the previous sentence, may say also of the same characteristic.
Aha, yes, yes, you're right.
In this
Of a
case,
fixed characteristic. You're right, thank you. It's also what it says in my notes, but it didn't make it to the board. By the way, I'm happy to make I write out these notes, so everything I write on the board is in my notes, and if anyone wants my notes, I'm happy to make them available. Okay, so this says that for a fixed characteristic, the theory of algebraically closed fields of this characteristic is complete. Because things which are isomorphic are in particular elementary equivalent.
So this completeness of ACFP is a statement of like piano arithmetic, right? So in principle, it should be possible to prove it without choice, right?
Oh, yes, and I think my next proof will, yeah. Yeah. This was the first proof we obtained of this result in this course. I'm not saying it. So the reason why I said all this is because this is really something which is symptomatic. That okay, so what I proved here is that if you have isomorphic ultra products, your elementary equivalent. But the converse of this statement is a really useful tool in model theory, but it goes beyond the. Proving it goes beyond this course. But the Isler-Feller theorem tells you that if you have two elementary equivalent L structures, then there exists an ultrafilter U in some set lambda such that the corresponding ultra products are isomorphic. So up to taking an ultra product being elementary equivalent is the same as being isomorphic, and that's something which can very often help your life because it reduces questions of first order questions to actually questions about isomorphisms. So, proof not here. I look up a good proof. I actually don't know. There must be a good textbook source of this proof. I don't know where it is, where to find it myself. I look it up. Okay, so now I want to prove the compactness theorem using Washer's theorem. And to prove Washer's theorem, I haven't said anything about the proof of Washer's theorem. So you do it by induction over formulae. So you do it by a structural induction that a formula phi in n free variables yeah. It's satisfiable in almost all AI if it holds in it's satisfiable in the ultra product. And there's a proof of this in Marker's book. So this is Marker section 2.1. Marker's introduction to model theory. No, I think it's called model theory and introduction.
Yeah, I have a question about the statement of Washer's theorem. So, is U just any ultra product that's not principal?
Yes. Yes, and somehow it's hidden in the magic of this theorem that it doesn't matter which ultra product you take as long as it's non-principal. Okay, so what do I want to prove? I want to prove that so there's a convex theorem over there, if every finite subset of T is consistent, then T is consistent. Obviously, the other direction is straightforward. If T is consistent, this means that T has a model by definition of consistency, which means every finite subset has a model. So there's nothing to do. So assume every finite sigma in T is consistent, and now I need to find a model of all of T. So, somehow, I guess I'm leading up to this, so obviously I need to find a set and I need to define an ultrafilter on this set. So what's the set? Let X be the set of all finite subsets. No, selection of all. Set of all finite subsets of T. And now for a finite subset sigma, consider F sigma, which is the collection of all finite subsets which contain sigma. So this is delta in X such that sigma is contained in delta. And curly F, the collection of all of those. F sigma in X. Now, what you need to check is that this F, curly F, right, it's named F for filter, that this really is a filter. So, okay. So in order to do this, the crucial bit is to check that it's closed under intersections. That is closed under finite intersections. So you check this, and then this is a filter, and any filter you take, it will be. You can use Zorn's lemma to extend it to an ultra filter. Right, so this you need to check. This is a filter. Okay. And say it's an ultra filter U on X, and now I want to take for sigma, again, finite subset, let's A sigma be an L structure, which is a model of sigma, and now I want to take the ultra product of these, of all A sigmas along this ultra filter U. And consider corresponding ultra product. And now what we need to do, I need to check for every phi in my theory T that phi holds in the ultra product. Okay, so I take a phi in my theory T. I can look at the corresponding sigma, which just consists of the singleton sentence phi. I mean, the set just consisting of phi, the singleton sentence phi. Right, this is then the corresponding F phi must be an element of my. It's an element of my filter F, so in particular it's an element of my ultra filter. And because it's a filter, the set of sigma in X, such that A sigma model my sentence phi, this is a bigger set, so it must also be contained in the filter. So, and if it's a big set, it's contained in my ultra filter, and the ultra filter, right, it holds in almost all AI, so it must hold in the ultra product. So then product U A sigma models phi. By what?
So phi was is the sentence in the definition of compactness that you are assuming is sort of you're assuming is finally satisfiable, and you're trying to prove that it's.
Yes. Sorry, I should have said what phi is, right? Is that what you're saying?
Yeah, you're trying to prove compactness. So it's the
Yes. So
the statement in the definition of compactness.
Yeah. So sorry, I want to say. I really want to say the ultra product I've taken here is a model of the whole theory. And in order to do this, I check for every sentence phi, which is an element of my theory, right? This theory is a collection of sentences that holds in this ultra product. But it holds in this ultra product just straightforwardly by construction and somehow unrolling the things I've encoded in these, which I encoded in these F phi's, because F phi, so the collection of things which so the collection of subsets of X which contain phi is large, so must be my ultra product, so must be almost everything. My ultra product standards. Almost dry. Okay, so this finishes. When did I start? At 4, right? Still have 25 minutes or so. This finishes my first section on the compactness theorem.
So the almost all in the theorem just means for a large set in that filter?
Yeah, it means all but ultra filter many. Yeah, I mean it holds. It means it holds for the indices where it holds is in the ultra filter. So now, starting my second lecture, just in case which is on quantifier elimination. So the underlying question is, given an L structure A, can we define the collection of sets cut out by first order formula? And in Bjorn's talk earlier, this was somehow, in some sense, if you look at existential formula, it's, if you look at the Diophantine sets, it's about existential formula in the language of rings. So here we are asking ourselves, so can we describe starting with an L structure A, can we describe a set of all subsets of A to the n for a given arity n such that A says, which are cut out exactly by some formula phi. So phi holds for an n tuple A1 up to AN in A if and only if A1 up to AN element in B. Okay, this will happen. And I mean, by doing some, so earlier when we looked at for example, when we looked at the language of ordered rings, whenever we have an ordering, what we can certainly define is intervals. Right? And what we can always define might be, intervals maybe with so far, the way I've written it so far, maybe in the reals as an ordered field, you can define intervals currently with, first of all, with endpoints in the integers, because every integer you can define as 1 plus 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 1 some number of times, or the negative of that. And then from the integers, you can straightforwardly define the rationals too. So certainly somehow in the ordered field of real numbers, we know if this is my notion of definable sets, all in the real line, all intervals with rational endpoints are definable. And maybe we can look at the real numbers and add constants for every real number, right? We can look at the real numbers as an ordered field and add constants for every real number. Then we can also define intervals with real endpoints and any point in the reals. Because I can just say I'm equal to whatever, pi. But a priori, both in the reals or in algebraically closed fields, this family could get arbitrarily wild. I mean,
Are you saying describe the set of B such that there exists a P?
yeah. Sorry. With maybe. Okay, and so what I just described in the reals, right, by using the order relation, what happened there was that I said, well, the order relation will certainly give rise to definable sets, and if I'm lucky, there's nothing else. And in the reals, it will at least tell you that this is the case. But and when we have some control over the definable sets, we usually phrase this as a quantifier elimination result. So in L theory T, you'll see in a moment that quantifier elimination will give us some sort of control, and then elimination if for every L formula phi of x1 up to xn, so for every n and every L formula in n many variables, there is a quantifier free L formula rho in the same number of variables such that T says the two are equivalent. Phi of x bar holds if and only if rho of x bar holds. Okay, what's the quantifier free formula? Well, I mean, I defined a formula as strings of strings of symbols, and quantifier free just means no quantifier appears in my string of symbols. So let's look at some edge cases. What happens if n is equal to 0? So this is for all, the statement should be read for all n. So for every n in n and every L formula, phi of x1 up to xn. So really every formula is equivalent to a quantifier free formula. So what happens if n is equal to 0? So if I have quantifier elimination, every sentence, right, 0 free variables, sentence means no free variables, is equivalent to a quantifier free sentence. Modulo my theory. Right here, this is modulo T. That's what I mean by modulo T. Okay, but what happens? I mean, what are the quantifier-free sentences? Well, maybe in the language of rings, I can think of several quantifier-free sentences, right? I can say something like 1 + 1 = 0, that's quantifier-free sentence. But if my theory has no constant symbols, there are no quantifier-free sentences. So, if L contains no constant symbols, and so by convention, that's something I've not yet told you, but if L contains no constant symbols, there's two quantifier-free sentences, namely top and bottom, true and false. Then top, so sorry, this is top, looks like a T, and bottom are the only quantifier free sentences. So top, right, is the true statement, and it's given by the empty conjunction. You want to see how it's a string? It's the string which is the empty conjunction. And bottom is the false sentence, which is equivalent to the empty disjunction. So these are somehow sentences which, by giving you only a vague definition of formulae, I've not covered these edge cases yet, but now please believe me. Okay, so if every sentence now in a theory without constant symbols, if now every sentence is equivalent to top, right? This means the theory is consistent. It always holds in all models of T. Every sentence is equivalent to true. Sorry, this means the theory is complete. Sorry, this can't be true, right? Sorry, if every sentence is equivalent to true, then the theory is inconsistent, because then phi and not phi are also, sorry. So I want to say, let me just write down what I want to say. So T is either complete if the assignments of things being true and false make sense, or inconsistent. If it does, right? If you assign a statement and its negation to the statement and its negation are equivalent to either top or bottom, then they're both equivalent bottom. Okay, and previously I talked about that model theory is about you might be interested in certain structures, and then you talk about their theory, and you might be interested in certain theories and talk about their structures. So here, for quantifier elimination, it really matters, the language L really matters. So quantifier elimination is language sensitive, in the sense that if you don't care about the language, any theory has quantifier elimination. Okay, maybe, yeah. Let me write that down. So if you're willing to increase the language, if you don't care, and if you really don't care, you can always obtain QE. How does it work? So I start with an L theory T, and then for every L formula, phi of x1 up to xn, we add an n-ary relation symbol. This formula may have quantifiers, but I just brute force it to not have quantifiers by adding a new symbol for it. N-ary relation symbol R phi, and we interpret it in the way you, right? I mean, R phi holds for a tuple if and only if. So let me write this down. Consider T expanded by all axioms of the form for all x1 up to xn, phi of x1 up to xn holds if and only if R phi holds. And so I brute force R phi and phi to give me the same set. Then call the resulting theory. This is now in a bigger language, right? Tm, and this M stands for the modularization. So then, any model of this theory, Tm is in particular a model of T, and any model of T can be expanded in the obvious way to a model of Tm, or uniquely to a model of Tm. And as we'll see in a moment, I'll give you a quantifier elimination criterion in the not too distant future. And from this you can deduce straightforwardly that Tm has quantifier elimination. So just asking that your class of structures has quantifier elimination in some language really doesn't make sense. It's not a suitable question. What you want is in some language which is nice, right? I mean, maybe which is already the language of rings. Well, it will turn out a theory of fields has quantifier elimination in the language of rings if and only if it's the theory of algebraically closed fields, or maybe the language of ordered rings. Well, I'll tell you some more quantifier elimination results as we go along. Okay, so the first thing we notice is that we only need to care about, I mean, if we want to prove quantifier elimination, it suffices to look at simple existential formula. A simple existential formula in language L has the form phi of x bar is, there is a y rho of x bar y, like where x bar, I mean where bar stands for finite tuple, with rho of x y quantifier free. Okay, and so simple existential just means one existential quantifier. There's exactly one quantifier, it's at the beginning and it's an existential one. And it ranges over exactly one variable, because previously I was cheating and I wrote many variables after my existential quantifier. That's not simple existential. The straightforward lemma is T has QE if and only if every simple existential formula is mod T equivalent to a quantifier free formula. So let's check this. So what you have to believe me, what I don't want to do, or where you have to do an exercise if you don't want to believe me, is that you can, whatever your formula, you can always draw all the quantifiers to the beginning and obtain an equivalent formula. And I mean, somehow you might have to, substitute some variables in order to not run into problems, but that's called pre-next non-net form. So, given an L formula phi of x bar, write it in pre-next non-net form. i.e., without loss of generality, phi of x bar has the form some quantifier, some finite number of quantifiers go up to m, and then some other symbol psi of x1 up to xn, y1 up to yn. Okay, and with each of the qi are quantifiers, right? They're either existential or universal quantifiers. Okay, and now what I want to do, I guess again I only have to prove one direction. if T has QE, then in particular every simple existential formula is equivalent to a quantifier-free formula. So I need to prove the converse. I need to prove if every simple existential formula is equivalent to a quantifier-free formula, then every formula is equivalent to one. Okay, and I do this by induction on M. So the base case, when M is 0, well, then there are no quantifiers. All is well. So how do I reduce M by 1? I mean, I guess I do an inverse induction. So how do I reduce M by 1? Well, I look at this formula. If Qm is an existential quantifier, by the assumption, this is a simple existential formula. So by assumption, this formula, the green formula, is equivalent to a quantifier-free formula, and I have one quantifier less. Right? So if Qm is existential, I can reduce the number of quantifiers needed by 1, and so by induction I'm done. I guess I also have to treat the universal case. So if Qm is universal, well, but then the negation of the green formula is an existential formula. Right? And so the negation of the green formula is by assumption equivalent to a quantifier-free formula, but the negation of a quantifier-free formula is quantifier-free. I'll just negate twice. So this is equivalent to quantifier-free mod T proceed by induction. Okay, so now I guess I have I have 5 minutes. What can I do in 5 minutes? So now using, while I wipe, I get myself a bit more space and so while I wipe, note that from this lemma you can deduce that Tm has quantifier elimination. And because why is this not immediately obvious? Well, because after what I did in order to go from T to its modelization is I introduced all these new symbols. And I know every formula in my theory T before. This is now equivalent to a quantifier-free formula, but now I have all these new relation symbols, and I of course can turn them into new formula. And I can use quantifiers, and what do I do? But the point is that if you take a simple existential formula, right, what can feature in the quantifier-free part, this will be a Boolean combination of quantifier-free formulas from my previous language, from the original language, plus these new relation symbols. But each of the new, so it's straight. You can easily see that your simple existential formula are all equivalent to quantifier-free formula, and then you're done. So I want to write down the theorem with which I will start next time, namely a criterion for quantifier elimination. For a theory T, the following are equivalent. A, T has QE. I mean, I guess I should say for an L theory T, because as we just discussed, the language really matters, so I shouldn't drop it. And B, for all models M and N of T, so structures are called A and B, maybe A, B, C if I need 3. Models are called M and N. With common substructure, A, and all phi of x1 up to xn simple existential elements A1 up to AN in A, the underlying set for my substructure. We have M says that phi of A1 up to N holds implies that N says the same holds. So a simple existential formula with somehow parameters which live, evaluated at elements which live in both structures, M and N. If it holds in the one model M, it must hold in the other model N, right? I guess, right, this is. So if there is something here, right, a simple existential, if there exists something here which stands in a certain relation, in a quantifier-free relation to my friends from A, then something must exist on the other side, M as well. And so normally, I said at the beginning of today's lecture, I said this morning, that structures are never allowed to be empty, but for this quantifier elimination criterion to work well, I need to allow the empty structure. So let me write this, and then I finish. So if L has no constants, then A is allowed to be the empty structure.
So why do people not allow the empty structure to begin with? Is it just a historical thing? It's just that somebody came up with the wrong definition and everybody stuck with it?
I think you can just do model theory allowing the empty structure or not, but as with this quantified elimination in the edge case n equal to 0, you just always have to think whether the statement is still true for the empty structure.
So then,
I'm not sure whether allowing the empty structure as a structure generally makes things better. I think not.
For example, Walsh's theorem is false.
Yeah.
For every x phi implies there exists an x phi.
So I think on average, the cases where you need to add the empty structure is smaller than the cases where you'd have to exclude the empty structure if you allow the empty structure as a structure. And that's the point. And you very rarely need to add it. Okay, so using this, we prove that the algebraic, I will not prove this. So as Sylvie said, you prove this via separation lemma, or you prove this via understanding what it means that something is, it's essentially a topological argument you need. But I'll not do it, but we'll apply it next time and we'll see it as our prototype for quantified elimination, I guess.